Welcome back. Today we're going to talk about the differences between quadratic, linear, and exponential functions. And we're going to see how we can determine, given from a table, what sort of function you have. Okay, so here we are looking at something called end behavior. So the end behavior of certain functions can be different, and that can allow you to determine whether the function's, for instance, linear or quadratic. So what end behavior is it's exactly like it sounds. It's the behavior at the end of a function. So as x approaches infinity, so we always think of it as the input value. What's happening with the output value when the input value is approaching infinity or negative infinity? So think about the x axis here. This would be infinity over here, and this would be negative infinity. So what's happening with the y values, or the values of the function, as x gets larger or gets very, very small? So there's notation for the end behavior, and it looks like this. It's using these arrows. So this is read as x goes to infinity. So this arrow is the words goes to. Oops. F of x goes to something. So either your choices of f of x could go to, the function could go to 0, it could go to infinity, or it can go to negative infinity, or it can go to another number like 3, for instance. What we are mostly going to see is we're mostly going to see functions going to either infinity or negative infinity. So another way of saying this is the function gets really, really large, or it gets really, really small. Okay, and then this notation is the end behavior going as x gets very small, or going to negative infinity. So this is read as x goes to negative infinity, f of x goes to, and you fill this in with a number. So both these things would be filled in. All right, so let's look at the end behavior of these two different functions here. Okay, so here is a linear function, f of x. So we would say as x goes to infinity, f of x goes to, okay, now as x gets really, really large, as I put in different values, 2, 4, 6, 8, 10, and so on, the function itself gets larger and larger values. So for instance here, this point would be, let's see, that would be 6, 6, right? So as the x value increases, the y value also increases. So another way of saying this is as x goes to infinity, the function value, or the y value, remember f of x is just standing in for the value of y. So f of x goes to, this should be an arrow here, goes to infinity as well, okay? Now, as x gets smaller and smaller, so as x goes to negative infinity, f of x for the linear function also goes to negative infinity, meaning it gets smaller and smaller this way, okay? And so that's one characteristic of a linear function. It's one, but there's other functions that have this characteristic and are not linear. Like a cubic function looks like this. Looks like an S shape like this. So as x gets greater, the function itself gets greater, and as x gets smaller and smaller, the function gets smaller and smaller as well. So we can determine, though, the difference between linear and quadratic, for instance, using this end behavior. Because quadratic, what's happening as x gets larger and larger, so for this branch right here, y increases as x increases. But for this branch right here, something very strange happens. As x gets smaller and smaller, as x goes to negative infinity, f of x also goes to infinity. So let's write this out. So in this right branch here, as x gets larger or goes to infinity, f of x also goes to infinity. But also, as x goes to negative infinity, the function itself goes to infinity. So meaning that's what happens. It goes and it drops down to the vertex, and then it starts coming back up again. So the end behavior for the quadratic function is very different than the end behavior of the linear function. And if I had an exponential function that looks like this, so exponential functions look like this, okay? We would say that as x gets larger, the function also, f of x also gets larger, goes to infinity. But something strange happens as x goes to negative infinity. Okay, so think about this. This would be like f of x is equal to 3 times x, or 3 to the x. So f of negative 3, for instance, would be 3 to the negative third, which would be 1 over 27, right? So this would actually get, and then 3 to the negative 4 would be 1 over 81, and so on. So this number gets smaller and smaller, and actually the numbers approach the x-axis. It asymptotes at the x-axis. We've talked about this before. So as x goes to negative infinity, f of x goes to 0. So this is the first time we've really seen this before, that the function itself starts to get smaller and smaller and smaller, and it gets into values that are closer and closer to 0. So if we graph this on a graphing calculator, here we would see that as, if we graph 3 to the x right here, let me just illustrate this. Okay, so it looks like here, it looks like it just starts right here, but if we go to the table and we start to investigate the values, so as x gets larger and larger here, y also gets larger and larger. So this is the concept, as x goes to infinity, f of x also goes to infinity. But if we look, as x gets smaller and smaller, look at these numbers. The y gets smaller and smaller and smaller, but it never gets to 0. So these right here are in scientific notation, meaning it gets smaller and smaller and smaller and smaller. Okay, but it never actually reaches 0. It just goes to, it approaches 0 is another way of saying it. Okay, so if you're given a table and you have to choose what type of growth is shown in the table. So for instance, there's 3 tables here. One's sort of being cut off, but we'll get to it in a second. And we're asked, is it linear, quadratic, or exponential? So those are the 3 we're going to choose from in Algebra 1. So given these x values here, what happens with the y values? Now the first thing that you should take note of is that the x values are increasing by 1. So the difference between these values is plus 1. So that's really important. It has to be the same. It doesn't have to always be plus 1, but the increase of x always has to be this. The same amount of increase, okay? Because then the trick that I'm going to show you right now will work. It doesn't work if the x's are increasing by a different value. So like if this increased by 1, the next one increased by 2, and the next one increased by 3, it would not work. Okay, but if you are saying like consecutive integer x values, then what we could do is we could look at the differences between the y's. So here, the difference between these 2 numbers is plus 2, meaning from one shift in an x value, there's an increase in the y value of 2. Here, this is also plus 2. Here, this is also plus 2. What I've just done right here, these subtractions, which right here it was 5 minus 3, here it was 7 minus 5, and here it was 9 minus 7. What I've just done right here, these are called the first differences, right? Difference meaning subtraction, and first meaning it's the first time I've done this. If your first differences are equal, that means that the thing that you're dealing with is a linear function. Okay, so if the first differences are equal here, and in our case they are, they're 2, 2, and 2, right? Here are the first differences, 2, 2, and 2. If the first differences are equal, then it's linear. Now think about first being the same idea as having an exponent of 1. Okay, so what you've actually just done, 2 over 1, 2 over 1, 2 over 1, that's constant. That's actually just the rate of change or the slope. So here we would know the slope was 2. Okay, we could get the y-intercept by figuring out, well, if x is 0, what is y? Y would be 1. So actually I can identify this function right away. It's y equals 2x plus 1. Okay, just by looking at the slope. And the slope, remember, is the difference between y, the difference of y over the difference of x's. And here it's constant. And you know if you have a constant rate of change, that's a characteristic of a linear function. Now, for the next one, I'm going to get the differences here. This is 3, right here. This is 9. This is 15, and 49 minus this would be, let's see, that'd be 20, but it's about, 49 minus 28 is going to be 21, right? So the first differences are not equal, right? The first differences are 3, 9, 15, and 21. But when I do the second differences here, this is 6, this is 6, and this is also 6. So what I've just done is the second differences. And when the second differences are equal, okay, not the first differences, but when the second differences are equal, like what you just have right here, 6, 6, and 6, what you know is that it's a quadratic function, okay? Now, it might be a little harder to determine which quadratic function we have, but we have at least 3 points. Remember, 3 points is enough to determine the unique quadratic function. Now, what you could do is you could take these points and plot them on a graphing calculator to determine what you have for the quadratic function. Remember, if we go into Stat and Edit, we could put these lists in a table. So it would be 0, 1, 2, 3, and 4 here. And on the right side, we'd have 1, 4, 13, 28, and 49. Okay. Now, in order to figure out what sort of quadratic equation is, I could actually ask the calculator to run regression. So second stat gets me, stat and go over to calc rather. And you want to do a quadratic equation number 5 here. I know it's going to be quadratic because its second differences are equal. And I can say, okay, the x list is L1, the y list is L2. And if I wanted to, I could actually store the calculator in Y1. Whoops. Let me get back to that menu again. Alpha trace gets me YY. Whoops. 5. Okay, here I can store the regression equation when I get it into, you want to use alpha trace, and that store it as Y1. Okay, and I want to go down to calculate. And here it gives me my A, 3, my B is 0, so what this is 3x squared plus 1. So this right here would be y is equal to 3x squared plus 1, okay? Because that's what the graphing calculator is saying right here. And that's actually stored here, so if I wanted to look at the graph right here, I could do that. And then if I look at the table, my values right here are going to match the values that I see in the table to the left, right? So 0, 1, 1, 4, and so on. Okay, so the next problem right here, so here I'm going to find the first differences is 500. My first differences are 500, 1,000, and 2,000. And when I find my second differences, 1,000 minus 500 is 500, but 1,000 minus 1,000 is 1,000. So here, my second differences aren't equal. My first differences are not equal, and my second differences are not equal. Okay, so in this situation, when the first and second differences are not equal, what you want to think about is the common ratio. Now, you learned about this when you did exponential functions. So the common ratio is when you take one x value, it's like y sub 2 divided by y sub 1. In other words, 1,000 divided by a previous y value, which is 500. So here the common ratio is 2. Now, is that the same? Well, if I take 2,000 and I divide it by, let's see, 2,000 divided by 1,000 is also 2, and 4,000 divided by 2,000 is also 2. So here, the first differences aren't equal, the second differences are not equal, but the common ratio is equal to 2. So you know that it's actually an exponential function. Okay, and what I could do is I could figure out you know a way to figure out the exponential function given the initial value, which is 500, and the common ratio, which is 2. You can figure that out. You can also put it into your graphing calculator and actually ask it to fit a exponential function to that. So if you go into Stat, go into Edit, you want to clear this out by going up to the x value, Stat, and Edit, and you want to clear out, hit clear and enter, and also up here, go up, clear, enter. You can put these numbers in, 0, 1, 2, and 3, and go over here and put 500. So if you forget how to get the exponential function, you can always just fit a regression to it. Let's see, 2,000 and 4,000, okay? And then what you do is go stat, go over to calc, and you want to fit a, let's see, exponential regression right there. Right here. So option 0, X list is good, Y list is good. Let's store it in alpha trace 1, Y1, and calculate. Okay, so it's saying that the initial value is 500, which we knew, and the B value, the value that's being raised to the exponent, is 2. So here, all you're doing is putting these into A and B. So it's Y is equal to, so it's Y is equal to 500 times B to the X. Finally, let's say that you were just asked to determine whether the points that you were given fit a certain model, like is it linear, quadratic, or exponential. Those are the options that you have at this point in Algebra 1. So here you have these points, 3, 9, 4, 16, 5, 25, and 6, 36. So the first thing I would do is I would actually just put it into a table. So we have 3, 9, 4, 16, 5, 25, and 6, 36. Now here, I can determine which model, like if it's a multiple choice question and it's just, is it linear, quadratic, or exponential, I can determine it by looking first at the first differences, right? This difference is, 7 rather. Okay, so 16 minus 9 is 7. Then here, 25 minus 16 is 9. And here, 36 minus 25 is 11. So here the first differences are not equal, but the second differences are equal. So since the second differences are equal, then we know that it's a quadratic equation. Okay. Now, we could determine a quadratic equation using some of the algebraic ways that we know how to do it, or we can just pick up our graphing calculator and ask the graphing calculator to run quadratic regression on it. So if I go to stat and edit and I put these numbers in, so we have 3, 4, 5, and 6 right here. And here, I can just overwrite these. If I could clear it if I wanted to, or I can just go and enter down into the entries here and overwrite. So for instance, if I put 9, it's just going to write over what I had before. So 9, 16, 25, and 36. It's a quick way of getting the equation here. And it works for linear, quadratic, or exponential. You just have to, once you've determined which type of equation, you just have to tell the calculator to run regression on it. So you go to calculator, and I'm going to go to quadratic regression, which is 5. And remember, if you want to store it, it would be alpha trace, and you want to store it in Y1 so that you can see it if you need to. So here you press enter, and it gives you the A, B, and C. So here it's just the A is 1. So here it's just Y is equal to X squared. And I guess we could have seen that too if I had just kind of looked at it, right? Y is equal to X squared. So it was it's a long way to just realize that like it's all you're doing is taking the X and squaring it. But that's the way you can determine whether it's linear, quadratic, or exponential, and then if you need to, you can find the functions. And that's the end of the lesson for today.